as a part of the push for Ethereum 2.0, developers, sorry, I got my notes just disappeared behind Zoom and I'm lost. Just give me 1 second for technical difficulties. All right, thank you. So as a part of the push for Ethereum 2.0, EIP44s would add pruning historical data in Ethereum clients. And the problem that it's there to address is that the state required to run a client to verify the chain is currently over 400 gigabytes, and it's getting larger all of the time. So typically, if you want to run a light client, or well, a client that verifies the chain, it would require a 1 terabyte disk to run. And a part of the Ethereum ethos is that anyone should be able to validate the chain on consumer grade hardware. The way things are looking, they're soon going to be pushing the limits of what could be considered to be consumer grade, right? A 1 terabyte disk is not something that everyone has. So the idea then is to prune any state older than 1 year in Ethereum, which is no longer required to validate new blocks. This turns out to be more than half of the state eligible for pruning, so it would reduce the hardware requirements from a 1 terabyte disk to a 500 megabyte disk in the short term, and probably ongoing due to other reasons. And this ties back into Ethereum 2.0 because they want to be syncing from something called a weak subjectivity checkpoint, instead of syncing from Genesis all the time, which is like a fast forwarded part of history. It's kind of the same thing that we talk about when we talk about warp sync for subgraphs. And using weak subjectivity checkpoints is required for the security model and proof of stake and Ethereum 2.0. So what does that have to do with the graph? Once Ethereum clients no longer store historical date that's older than 1 year, they will also be unable to serve queries for that state. And prominent voices, excuse me, in the Ethereum community, including Vitalik himself, have publicly endorsed the graph as a replacement for the JSON RPC API in Ethereum to query this historical data. In fact, the graph is mentioned even in the text of EIP44's proposal for this purpose. So there are 2 things that would need to happen though for DApp developers that are still relying on the JSON RPC API to be able to have a smooth transition over to using the graph to serve that data. The first thing that we need is something called the Ethereum network subgraph. And someone in the community would need to build this, maybe a core dev, maybe a grant, or whoever. But what that would be is, instead of building a subgraph for the specific purposes of a DApp, we would build a subgraph that is able to index all of the sort of data relevant to the Ethereum chain in an agnostic way, and thereby be able to mimic the JSON RPC API. So you would be able to query things like logs or account balances or receipts or all that information. It might require some updates to graph node in order to be able to support this. I'm not sure. I know that's something that we looked at a long time ago, but we need to dig that out again and pick that back up. The second thing that needs to happen is to keep the trust model the same for the DApp developer. We would need to move our verifiability story to a 1 of n model. That's the same trust model that a consumer would rely on for ensuring the liveness of light clients. So we need to have that same level of trust for all of DApp developers to feel comfortable migrating from Ethereum to the graph, both for the whole story of verifiable indexing and verifiable queries. We don't necessarily need all of our feature set covered by 1 of n trust model just yet, but at least everything that would be used by the Ethereum network subgraph, and to be able to mimic the same queries. So at least say verifiable queries for like get by ID would be useful for things like account balances, but not necessarily features like where and skip and more complex features. All right, so to give you an idea then of where we're at, like what is a one of n trust model in relation to the graph, and what needs to be implemented to get there. It'll give a light overview of the stages of verifiability that we have in the graph. Basically, in order to allow us to both develop quickly and have high levels of security, we move different features through a pipeline of verifiability stages where they start with higher levels of trust and then end on validity proofs, which require basically no trust at all. If you have a trusted block hash, then you can get all of the other information that you care about from the indexer, so you don't have to trust anyone. Those stages are experimental, arbitration, fraud proofs, and validity proofs. And in the first stage, experimental, is generally reserved for features that are not fully implemented. Maybe their API is not fleshed out yet, or there's debate around what the right API should be. They're sort of unstable, or maybe they have a outsized difficulty in being able to make the feature deterministic. So things like full text search or IPFS data sources, or rather file data sources, fall into that category. And then a feature that is in the experimental stage cannot have its security guarantees enforced by the protocol because it's not deterministic or what have you. So you can't say compare attestations. Instead, a consumer needs to rely on the reputation of an indexer. So what they might do if they're relying on an experimental feature like full text search is maybe not use that feature in production, or maybe be sure to select indexers which are long-term incentive aligned with the protocol, so that they can rely on the reputation of that indexer. It's not where we want any feature to be. Ideally, we're moving things quickly to arbitration. And in fact, most features are in the arbitration stage today. The arbitration stage is when indexers sign attestations for things. This is query attestations and it's proofs of indexing. They sign these commitments to data, which can be brought to the chain and shown in a dispute. And then the arbitrators, which are elected by the Graph Council, will then verify that that work has been done correctly, and there are penalties of slashing for not doing the work correctly. So that's a governance model. You have to rely on the arbitrators basically to be active and honest participants. From there, we would like to move to fraud proofs, and fraud proofs are the one of n model, where instead of necessarily relying on governance, any participant, if there's at least one participant in the network that is active and honest, then they can force everyone else to also be active and honest. They usually do this with something like a refereed game, maybe in the style of what Arbitrum has, where you can bisect computation and play out this little game that will surely tell you if one of them is correct, they'll be able to always win that game, and then the loser will be slashed. And so those are pretty cool, and it's something that we've been looking at for a long time for indexing. That's one of the reasons that our subgraphs are compiled to WASM, actually, is because WASM is amenable to these fraud proofs. The next stage, which is the highest stage, which doesn't even require one of n, it's just fully trustless, is validity proofs. And with validity proofs, you're able to show the consumer somehow that the computation has been done correctly. One technique that we use for this is ZK snarks, and like Merkle proofs are actually a form of validity proofs. But generally, the idea is you try to provide some succinct amount of data that the consumer can then verify that the computation is done correctly. So to get everything to the one of n model, we need at least fraud proofs, which is going to be our targeting, what we target in the short term for indexing. And then we can have anything fraud proofs or higher. So we will do validity proofs for queries, because this validity proofs is something that we've been working on for years now at The Graph. We've been investing ahead of time, realizing that that was going to be an important component of Web3. So rather than do fraud proofs as an intermediate step, we'd like to then just bring validity proofs to production and to support queries. And the update on that is that the Roadrunner snark, which is the snark that the Snark Force has been developing for Scalar, is nearing the design freeze. We'll be pulling in Ariel to help us do things like compare the verifier gas costs on L1 and L2. And once we kind of confirm that what we have made is going to actually be efficient, then we'll be able to freeze the design on Roadrunner. And the Roadrunner snark, it turns out, it was built for Scalar, but it turns out to be applicable to verifiable queries as well. So our next step there, once we finalize the design of Roadrunner for Scalar, is to then split the design team from the implementation team. So the implementation team can get Scalar over the line and into production, while the design team then moves to adapt Roadrunner to verifiable queries. And so that's kind of what we're all doing to help move EIP44s forward, and to make sure that the graph is a necessary part of the DApp developer experience.
Amazing. Thanks for sharing, Zach. Very nice. I think that's a good segue into Semiotic. Sam, who's been working with us since wave one. Maybe we can share exactly what the team has been working on, and just do a quick intro on particularly this, what you just called Snark Force, which is actually a name that I quite like. Sam, will you be up to do a quick update here?
Sure, Pedro. So
Thanks.
I'm going to just give a little background on Semiotic, because so we're going to be working with Zach and the rest of the team to. We've been working with Zach and the rest of the Snark Force team to design the new Roadrunner snark. So I'm just going to give you a little story, a little bit of back history about us. We were co-founded, or we were founded 2 years ago, and we have four co-founders. Three of us we all come from R&D. So three of us have PhDs, and the fourth one was working in R&D as well. And just as a little, we were doing industrial R&D specifically. So when you hear R&D and you hear PhDs, you might think academia, and academics are publication driven. So that's how their careers progress, is through getting papers. Industrial R&D is more focused on delivering maybe proofs of concept or pushing things into production. So for example, and specifically, so where do we come from? So half of us came from an AI background, and the other half of us came from a cryptography background. I actually have experience and education in both. So Gokai Saldamli is one of our co-founders. He's a cryptographer. He's also a professor at San Jose State University. And prior to San Jose State University and Semiotic, he was at Samsung. And at Samsung, he designed their core IP for their cryptographic hardware accelerators for their SIM cards. So he did the Verilog, which is a hardware description language. He wrote all of the Verilog for their cryptography accelerators, and then he had that Verilog deployed in billions of devices. So he's like this hardcore mathematician, implementer guy. And I just wanted to give you, a feel of that the sort of team that we're trying to build, or that we are building. And then, so maybe let's go to the Okay, so just to kind of complete the story. So for the first year of the company, we focused on fully homomorphic encryption. So specifically what we did was we were building a tool that was to be deployed in the cloud for encrypted machine learning as a service using fully homomorphic encryption. So what is this homomorphic encryption? At a high level, it lets you compute directly on encrypted data. So for example, let's say you had A, where A is some number, and I encrypt it, and I have B, and B is some number, and I encrypt it. I can send you A and B, and you can add them and you can multiply them. But you can never know what A is or B is or any intermediate result. And through addition and multiplication, you can actually do a lot of sophisticated things. For example, you can evaluate deep neural networks for me. So you can do all the work for me, and so I can outsource it to you. And then you never see any intermediate results. You can send it back to me. So we did that for a year. We got attention and money from the government, from the military, but not a lot of traction from industry, because their industry is mainly driven by regulation, and regulations don't cover currently homomorphic encryption. So then we started working, after about a year, we started working with the Graph. We were part of the Wave 1 Graph grants, and we focused on reinforcement learning initially. And then after that, we started expanding into cryptography, really with Zach being the champion for that. And so now we have 3 people that are working full time with the Snark Force, and this team, like Zach said, the Graph and EduNode has been putting a lot of effort for several years into planning for where we are now. And so what we bring is a solid background in understanding cryptography and cryptographic primitives. And you should see it, the field of snarks and zero knowledge proofs. This field is exploding right now in terms of academic ideas and progress. And the Snark Force is at the bleeding edge of integrating what is just becoming theoretically possible. And they are making they're turning it into a practical system. And it's going to be, it's at the leading edge of Snark designs. So I think I'll stop there. We're super happy and excited to be working on this, and it's going to be a big deal when it's deployed.